Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures, we have discussed the quantum mechanical solution of angular momentum operator. We have defined the angular momentum operator in Cartesian coordinate and in spherical coordinates, and then we have looked at its solutions, that is eigen values and eigen functions of this angular momentum operator. In today's class, we will start discussing about a few simple systems where we can see the application of angular momentum operator. In the course of this discussion, our first example that we will be dealing with is the so called particle on a ring. You remember we discussed particle in a box problem, where the particle was confined to a one dimensional box and later we extended it to two dimensional and three dimensional box. This is somewhat similar, however, instead of having a linear translational motion, here in this case the particle is on a ring and is showing a rotational motion. That is the key difference. When I can show the movement of this particle on a ring here, where you can see that the particle with mass m is going around this circle of radius r. When this happens, you can see that if I define this axis as my x axis, the particle while going around this ring, it makes an angle phi with respect to x axis, the Cartesian axis x. So, this value of phi will be from 0 to 2 pi. This is when I describe the motion of the particle in an angular coordinate. However, when I describe this particle's motion in the Cartesian coordinate, you can see that I have defined this axis as z axis, this is x, the other axis is y. So, therefore, the movement of the particle is confined to x and y axis, or in other words xy plane. So, for such a system, if I have to write down the Hamiltonian of the system, because I want to solve this problem quantum mechanically, the particle and a ring problem. So, I would start by writing down the Hamiltonian. The Hamiltonian will have two terms, one kinetic energy term, another potential energy term. Remember, this Hamiltonian is the overall energy operator, and what I am saying here is that the energy will have two components, one coming from the kinetic energy, because there is a particle which is going around, which is showing some movement, and then there is the potential energy. Like the particle in a one dimensional box problem, we would assume that this particle, when it goes around this ring, it experiences no other interaction. So, therefore, its net potential energy is 0. So, therefore, my Hamiltonian has only kinetic energy operator, because I define my potential energy as 0. So, suppose this is we are assuming that this is an isolated particle, it experiences no other external potential. So, this is my kinetic energy operator. Given the mass of the particle, I can write down the Hamiltonian now in h square by 2 h bar square by 2 m. Here m is the mass of this particle, and then I have d square by dx square plus d square by dy square. I am stopping here with x and y, because I see the movement of the particle is all in the xy plane. So, that since the z axis is not activated here in this problem, so therefore, I am writing down the kinetic energy as minus h square by 2 m and the square second derivative with respect to x, second derivative with respect to y. Please note, since I have both x and y axis are operational, so therefore, instead of using a normal derivative, I am using partial differentiation over here. So, this is my kinetic energy operator, and which is also the total Hamiltonian. Now, you see, with this kind of operator, I could have used this operator to describe what, suppose a particle is going along a square or a rectangular box. However, in this case, it is going along on a ring. So, it is showing a circular or a rotational motion. So, therefore, I already know that I can convert this Cartesian coordinate to spherical coordinate. So, since I have only 2 dimensions here, one is r, another is phi. If you remember the theta, the azimuthal angle, that is still not operative here, because the movement of my particle is only along the xy plane. So, therefore, I know from here I can see that x I can define as r cosine theta and y as r sin theta. If I use x and y on this form, then I can write down the d square by dx square and d square by dy square as forgive me, here this should have been phi instead of theta, which so x is given as r cos phi, y is given as r sin phi, and this term which is appearing in the Hamiltonian can be shown as a combination of these 3 terms, where I see that is second derivative with respect to r, first derivative with respect to r, and second derivative with respect to phi. These r and phi are the 2 angular coordinates that I have in my system. Now, since the particle is only going around this ring of a fixed radius r, so therefore, when I have this first 2 terms in the kinetic energy operator, which requires a differentiation of with respect to r, these 2 operators are not going to give me any result, because the overall wave function has to be confined to a fixed value of r. Since the motion of the particle is on a ring with fixed radius r, so therefore, these 2 terms on the kinetic energy operator and therefore, the Hamiltonian operator can be ignored. So, when I ignore these 2 terms, the Hamiltonian that I wrote here becomes I am moving from partial derivative to normal derivative, because I see that I have only one coordinate operational here. So, this is the mass of the particle, and this becomes the overall Hamiltonian of the problem. Now, we have to, when we have written down the Hamiltonian, we would now like to solve this problem quantum mechanically. So, to do this, I would write down the corresponding Schrodinger equation. Suppose I say this is the Hamiltonian. Suppose my psi is the eigen function with an eigen value of E. So, I am writing down the Schrodinger equation corresponding to this operator Hamiltonian. So, now what we would do is that let us use this expression that we have. Or we can simplify this So, where I have made all the term the second derivative term without any prefactor, and all these prefactors are converted here. So, I can simplify this one more step. I can define when I have this mass and r square. So, this is simply the moment of inertia, where I the moment of inertia is defined as m r square, where m is the mass of this particle going around a circle of radius r. So, now I have this second order homogeneous differential equation, which something similar we also saw in particle in a one dimensional problem. If you remember the solution of this, you will see that the solution of this differential equation is essentially an exponential function, where the exponent is given as the square root of this term over here. Multiplied by the coordinate. So, this is one solution. The other solution could be the negative of it, simply. So, now I got two possible solutions. I could write this as e to the power plus or minus I, this term over here, and phi, where phi is the angular coordinate of my system. So, here, since I have such a big term here, I would replace this function by, I will give a somewhat a shorter name to it. I call it m. I still do not know what is this m, but this m depends on the moment of inertia, which depends on the mass of the particle, the radius of the ring around which the particle is going, h bar, and the energy of the system that would come out of the solution. So, now what I have is that I have got this wave function, which is e to the power, in short I can write e to the power I m phi. So, this is the general form of the wave function I am getting. Now, we would see, if you remember our discussion for a particle in a box problem, we obtained a general solution of the wave function, and then we imposed the boundary condition. And for a particle in a box problem, the boundary condition was the wave function should be continuous at the boundary of the box. Here, now we have to see some boundary condition. What kind of boundary conditions can we imagine here? One thing that we can notice here is that when I make when the particle makes a 2 pi revolution and comes back to this original position, and for the second part, when after making the 2 pi revolution, the wave function should reproduce itself. The wave function should be single valued. So, that means there should be a periodic nature in the wave function. So, that we will impose on this wave function, and we will see what is the outcome of this discussion. So, we have now psi as a function as e to the power I m phi, where m is defined as h bar. Now, this is psi as a variable of phi. What I just suggested is that psi of phi should be equal to psi of phi plus 2 pi. So, that means when I make a 2 pi revolution, and come back, the wave function should reproduce itself. So, when I look at this, I write down the right hand side e to the power I m phi, and here I m phi plus 2 pi. All right. So, now when I look at this right hand side, I have first term I m phi multiplied by a second term I m 2 pi. Now, the left hand side and right hand side can be equal to each other only when this second term in the right hand side will become 1. Only then this condition will be satisfied. So, let us impose this condition that e I to the power m 2 pi is 1. So, we know we can write this function as a cosine function plus a sine function. Sine function is with the imaginary root I, and this should be 1. Now, when I look at this, I can say that this equality will hold when m is, suppose if I use m is 0, then this function becomes, the sine function becomes 0. So, therefore, the imaginary part is gone, and I have, since I have 2 m pi, this becomes 1. So, this relation is valid when m is 0, and similarly I can show this relation will be valid when m is plus 1. So, you can see this will be sine 2 pi, this will become 0, and cosine 2 pi is 1. Not only that, I would also have minus 1 as a possible solution. that is because the cosine function is an even function. So, similarly, I can show that I have all other integers plus or minus n are allowed values of m. So, here if you see that I had this general expression for the wave function. When I started my discussion, I defined m as twice moment of inertia, the energy of the system h bar. Moment of inertia is product of mass, which could be a real number, which is a real number. The radius of the ring is again a real number, and h bar is again a constant. So, I see I had, when I looked at this number, I would not have imagined that this m would actually be an integer. But why do I get this the restriction that m has to be integer? That is because I have to make sure that my wave function is well behaved. When I say that, when I impose the condition that the wave function is well behaved, then that boundary condition gives rise to this interesting observation that the allowed values of m are going to be 0, plus minus 1, plus minus 2, plus minus 3, and so on and so forth. So, if m has some discrete value, so I can solve this now. I can rewrite this expression as E where m is 0, plus minus 1, plus minus 2, and so on and so forth. Here the energy of this particle in a ring turns out to be a function of m. So, this m goes from 0, plus minus 1, plus minus 2, and so on and so forth. We will now discuss a little more about these eigen values that we just discussed. So, we saw E m is m square h bar square divided by 2I, where m is 0, plus minus 1, plus minus 2, and so on and so forth. What is the lowest possible value of m? That is 0. When m is 0, E m is, I put here, so E 0 is 0, that is the lowest energy. If m is plus 1, then I see E 1 as m square, which is 1. So, I have h square by 2I. You see, when I put m as minus 1 instead of using m as plus 1. So, in that case also, since the energy has m square, so I will have E of minus 1 as same as E of plus 1, which is h bar square divided by 2I. So, I can write this E plus minus 1 have same energy. So, now I have one energy level where there are two different eigenfunctions. So, this energy level is twofold degenerate. Similarly, I can see when m is 2 or m is minus 2, I would have the same energy, that would be m square, which is 4 h bar square 2I. Again, this energy level is doubly degenerate. What we see here is that as I increase the values of m further and further, the energy is increasing, because this will simply become m square multiplied by this constant. This is a constant because h bar is the universal constant and I is a constant for the particular problem in our hand. So, therefore, the energy of the system would keep on increasing as I increase m value, but no matter what value of m I take, as long as m is not equal to 0, the energy levels are going to be twofold degenerate, or they are going to be doubly degenerate. What does that mean? When I look at the lowest energy level E 0 as 0, so here this I can say this is the lowest possible energy. So, I call this as 0 point energy. Now, you see we have a system whose 0 point energy is 0. When the energy of this system is 0, what does it mean? This simply means, remember, this energy that we have now is coming exclusively from the kinetic energy, because we have no other potential energy. So, therefore, if the energy of the system is 0, that means the kinetic energy of the system is 0, that means the particle is at rest, or it is the particle is stationary. So, the 0 point energy simply means when the particle is not moving, it is at rest at one point of the on the ring. But when I go to higher values of m, that would indicate that the particle is moving with higher kinetic energy, because as I see, as m goes up and up, I would observe that the energy of the particle is increasing. The particle in a ring moves around the ring with higher kinetic energy. But how do I interpret this twofold degeneracy of the energy level? I can say that when for any value of m which is not equal to 0, the particle, when it is moving around the ring, it can either move in clockwise fashion or anti-clockwise fashion. While moving at clockwise or anti-clockwise motion, the particle can have the same kinetic energy or same magnitude of angular momentum operator. So, keeping the same magnitude of angular momentum and same kinetic energy, the particle can show two different type of motion. One is clockwise motion, another is anti-clockwise motion, and this is seen for higher values of m. The higher values of m has simple effect that the particle now moves at higher speed. We will now discuss the eigenfunctions of the system. The eigenfunctions that we obtain are e to the power I m phi, where phi would go from 0 to 2 pi when the particle makes a complete revolution. But this function is not normalized yet. We will see how we can normalize it. So, this is psi star phi, psi of phi, d phi, and the phi goes from 0 to 2 pi. So, psi is e to the power I m phi, the psi complex conjugate will become e to the power minus I m phi. So, therefore, e to the power minus I m phi, e to the power I m phi, that will become 1. So, I have simply d phi So, if I had multiplied this as with a normalization constant n, I would have got n square here, 2 pi n square, which should have been 1, and in that case n would be simply 1 over 2 pi under square root. So, therefore, the normalized form of the wave function is now. I have come across a situation where the wave function is not actually real, but it is complex. It has, I can write this wave eigenfunction instead of e to the power I m phi, I can write it as a cosine function in the real plane and a sine function in the imaginary plane. So, I have a cosine function in the real plane and a sine function in the imaginary plane, and together I have this. So, but the eigenfunction of this particle in a ring problem is an imaginary function. I provided a visual display of the eigenfunction of particle in a box or harmonic oscillator. Now, if I want to do this for particle in a ring problem, how would I do this? Suppose instead of showing it in a ring, I unwrap that ring and stretch the ring to stretch the ring to a straight line, so that it goes from 0 to 2 pi, and at the center I have pi, and here it is pi by 2 and 3 pi by 2. If I have to draw this real part of the wave function, I have it is a cosine function. So, this would be this is the cosine function, where at pi when phi is pi, the function is minus 1, and at when phi is 2 pi or phi is 0, the function is at plus 1. I can, if I have to draw the sine function, the imaginary part of the wave function, it would be simply So, sin pi will be. So, I have a cosine function. So, this is the real component of the psi and this is the imaginary component of the psi, the wave, the eigenfunction. You see the real and the imaginary components of the wave function, they grow, they have a phase between them, a phase of pi by 2 in them. What you also notice is that where the the imaginary part is 0, the real part attains its maximum amplitude. If you take the probability density of this wave function, so which is, so this is my actually I am drawing this wave function for m equals to plus 1. So, if I have to draw the if I have to find out the probability density of this function, you would see that I have 1 over 2 pi e to the power I m phi, which is simply 1 over 2 pi. That means, the probability density of the wave function is does not depend on the angular coordinate phi, it simply remains the remains constant throughout the region. This is an important point. Other thing that you must remember is that when I increase the value of m, when I go to m equals 2 or m equals 3, you would see that I will have to fit in more and more number of wavelengths within the same length 0 to 2 pi. So, that means, for higher values of m, I will develop more number of nodes. Another important feature of this wave function is that when I know that this wave function comes back to its own form after 2 pi revolution. What happens if I change the wave function instead of 2 pi revolution, if I do it for pi revolution? So, I see that I will have e to the power I m phi multiplied by e to the power I m pi. Now, e to the power I m pi, if I had e to the power I m 2 pi, this function would have been plus 1 all the time, but e to the power I m pi is plus 1 when m is even and minus 1 when m is odd. So, that means, for an odd function, for an odd value of m, the wave function will be negative of itself after 180 degree of rotation. You can see this feature over here when I am plotting the real part of, suppose I am plotting the real part of the wave function corresponding to m equals 1. After pi revolution, I would be, if I start my point over here, after pi revolution, I would be at this point. So, I see that the wave function is negative of itself after 1 pi revolution, after 180 degree. But when I make 2 pi revolution, of course, the wave function is going to get back to its normal form. So, in today's lecture, we discussed about one important application of angular momentum operator, that is particle in a ring. We discussed its eigen functions and eigen values. We will continue our discussion on applications of angular momentum operator and other simple systems in our future classes. Thank you for your attention.